open, I guess, for people to.
Unless there's noise coming.
So it's an open door policy. All right, ladies and gents, welcome to this Thursday afternoon. My name is Jussi Mann. I come from across the road from VTT, where I currently work as I'm in charge of our research in bioeconomy and circular economy. So it's actually quite fitting title for my presentation. So for the next hour or so, I will try to explain to you those two concepts and what they actually mean in relation to energy system change. And what I'm going to talk is first just setting the scene, getting the definitions for you so you understand the big picture. And then, because this is actually a topic that could warrant a full sort of a seminar series of lectures, I'm going to focus on three things. I'm going to talk about biomass, the use of biomass, and how the resource efficiency requirements are affecting the way we see biomass, and especially how we see energy from biomass. The second I'm going to talk is the role of energy in circular economy. I'm going to talk briefly about waste to energy concepts and where they are heading in the future. And the third topic I will be touching upon is the use of CO2 as a raw material and how that links actually to the energy system change and also to bioeconomy. So it's about 50 slides, so take a comfortable position and I guess, I don't know what has been the habit here, whether you actually want to, if there's a question, just shoot a question, or do we wait until the end?
Whatever you want.
Actually, if you have questions, right, just ask when you feel like it. And there will be also plenty of time in the end to go through some of the questions.
Could you say something about the microphone? Because we are recording, we have to use the microphone.
So anyway, if you have a question, you need to use the microphone. Otherwise, the good people who are watching this online will not hear your question. They will only hear my answer. So that sort of comes a sort of a reverse problem type of, we know the answer, but what was the question type of issue. I'll start actually by, why I took this is basically how we at VTT see the world. We are here to focus on solving five major societal challenges. And I'm going to talk about the two on the top today. The climate action, so basically how to combat climate change, and resource efficiency, how to make one planet be enough for the human race, and we don't need 3 planets to satisfy our consumption. And actually the bioeconomy, resource efficiency, circular economy and energy system change are the nexus of these two things. And how we actually see the future in these topics is we first of all see, of course, there are, as you well know, there are changes coming in the electricity and energy system. We're starting to see a phase of electrification. Everything will be more electric than it used to be. We are starting to see intelligence getting into everything we do, also in the energy system. So basically the whole system becomes more intelligent when it comes to, for example, load demand and such things. And of course what we are seeing is that we are increasingly we need to get into low carbon electricity. And then we are talking about photovoltaic, we are talking about wind, we are talking about biomass. But also we are talking about nuclear. At the same time, we are seeing the fact that we need to conserve materials. We need to make sure that the materials flow longer in the cycle. So it's not, get the raw material, produce something out of it, use it and throw it away. We need to get into more cyclic behavior when it comes to material flows. What we need to do is to see that can we actually replace non-fossil resources with bio-based and renewable resources. And of course, looking at then what can we actually do with carbon? So these are the sort of the big questions out there. These are also the big opportunities out there that we need to solve. And I'm going to now talk about, especially about the renewable, the non-renewable and the carbon reuse economy, but keeping in mind that what is actually happening in the energy sector itself. And if I start with just briefly telling what bioeconomy is, or how it's been defined, it's basically, it's an economy that uses renewable natural resources to produce food, energy, products, and also services. So food is easy to understand, and that is the first priority, food first. We need to nourish the human race. Products, energy, but also services. The biological resources like the forests provide a lot of other services than just commercial services. There's recreational value. There's also the so-called ecosystem services, purification of air, purification of water, the bees pollinate, etc., etc. And what we're trying to do there is to reduce the dependence on fossil resources, so replacing fossil resources with renewable resources. But also, but also what we need to do there, and this is the ecological part, is also to make sure that we do not cause any biodiversity loss. So actually it is a fairly complex dilemma to at one point increase the use of the resources, but at the same time trying to improve the ecological state. And this is what actually strives us to look at the resource efficiency of the natural resources that we use. How can we make the best use of the natural resources so we can actually fulfill these goals, that we use more of it, but we use more efficiently, and at the same time we leave enough not to maintain a certain biodiversity and to improve the ecological state. Circular economy, another buzzword of the recent years, is actually an economic model where more or less we're trying to retain the value of material as long as possible. And this means that instead of, as a business model, instead of owning, you could be sharing, leasing. It involves reuse, repair, recycling, which means that actually you are trying to create an almost infinite or endless loop of material use and trying to minimize the amount that you throw away. And of course, at the same time, minimize the amount that you take into the material cycle. Are you familiar with the waste hierarchy? Does that ring any bells? Yes. So it follows the waste hierarchy. You have to, prevent, reuse, recycle, etc. And these two things actually are now very high also on political agenda. Especially in Europe, circular economy, it is actually driving a lot of policies at the moment. Because, first of all, Europe is a resource-poor area. So obviously what we're trying to increase is to increase our security of supply. Rather than have to rely on imported sources, we can actually keep the loops closed within Europe. Whereas when we're looking at countries like Finland, which have a lot of natural resources, we are heavily pushing for bioeconomy, where we're trying to use our resources to replace the fossil-based resources that we don't have. We don't have oil, but we have forests. How can we make forests to be the new oil? And actually, if you want to see it all in one big picture, I like this picture in a way that this shows also the loop that we're trying to maintain, the part of the circular economy. And one essential part of circular economy, and this is now outside the energy field, I understand, is how do you design your products? How do you design something to be easily replaceable, easily reused, easily refurbished? And then how you actually keep the loop. And in the middle you actually see the two different material flows that we have in this world. We have the renewable and non-renewable. And the same principle applies to both of them. We, of course, also with the renewable materials, we try to keep them in the loop as long as possible. But what we're also at the same time trying to do is to have the green part of the yin and yang to overtake the black part. So at the same time, keeping the loop, but also pushing the fossil resources or the non-renewable resources into a minor role in the world. And what we actually have on the clean tech, which surrounds sort of the material flows, is the technology layer that we have. Those are the technologies that make it happen. The production technologies, the recycling technologies, the separation technologies, the energy technologies that make it possible actually for us to keep these materials in flow, make it possible for us to replace materials with other materials.
Jussi, how do you see the social technical actually dimension? Talking about also, and including also
You just need to have the mic.
about that. That's a little bit like an economic and technical perspective, but if we take the socio-technical perspective and the behavior type of change, shouldn't those actually be also integrated in when we talk about and try to understand actually the circular economy?
Yes, and actually both of these. So basically, a lot of it is actually about the way we behave. Obviously, this is just these are the principles. And there are two ways that we can actually make this happen. The other one is that we voluntarily act like this. That all of us want to make the change voluntarily. And we demand for services and products that follow these principles. The other way, which is the more usual way, is that somebody makes us do it. So then we come into regulation or legislation saying that you will have to recycle. You cannot put anything in landfill anymore, etc., or there will be some taxes imposed on products that don't follow these principles. So basically those are the two ways that we can make the change happen. I don't know if that answered you.
Yeah, I think it's crucial.
Yeah, that is a crucial element, yes. It's very good actually that also you take the social aspect into, when I'm talking, I guess you are engineering students. And just to give an idea that basically what it could mean in practice, this is just actually from a vision document we did a few years ago on just showing what it actually means. These are how you can actually combine, and one part of circular economy when it comes to industrial systems. It's called industrial symbiosis. So the waste of one is the feed of another. And just to give an idea what kind of connections there could be in an area which has certain types of industries. So how you can actually feed in side streams and waste from one industry to another in order to close these loops. This just for illustration only, just to give an idea that what it actually could mean in practice. Right. Now I'll actually dig deeper into actually the use of biomass and also talking about what is the role of energy in this. And the question first is, why do we actually want to use biomass for? I mean, in the first place. First of all, if you look at from the climate point of view, biomass as an energy source is seen as carbon neutral. So there is definitely a climate effect that takes place if we use biomass. Secondly, which is most important for the politicians and also for employment, is that it's domestic raw material, at least in the case of Finland, and also in the other countries which have a lot of biomass resources per people. So it creates jobs. There's a trade balance. Those are basically the exports. So there's an economic and social aspect to this. The security of supply, it's domestic, and actually something that is not very often discussed, that actually biomass and biomaterials are, in some cases, are really excellent materials for certain applications. For example, for construction. Some of the oldest surviving buildings in the world are made of wood. And those are in places which have frequent earthquakes. Only the wooden structures have been able to withstand the earthquakes because wood is flexible. And if you keep it dry, it's more or less eternal. And if we are looking at that, if there is sort of a hierarchy, so if we have a limited resources of biomass, and just to give you an idea, that if we used all the growing biomass in the world, you know, everything that we use for for food, everything that grows in the forest and the fields, and if we convert that into energy, it will not satisfy the energy need of the world. So biomass is not the answer, it is part of the answer. And then we are starting to think about actually if biomass is a limited resource, what should we use that limited resource for? And then you start looking at, well, food and feed is obviously the top of the list. But the second is that really the products that somehow benefit from the structure of the biomass. It could be fiber, so composites, papers, packaging. It could be structures like the tables, the buildings. And then to products that replace fossil-based products. You know, replace plastic, replace certain chemicals with biomass. And then for energy. But the energy is the lowest ranking in that hierarchy. And also it's not only because we want it to be so, but it's also, if you start looking at on the sort of the pyramid, the higher up you go, the better price you get for your biomass. So it's also that you try to optimize the revenue that you get from your biomass by producing higher value, or you strive for higher value products. And the things that you cannot use for higher value products, then you will use for energy. Just an example, in Finland, if you want to buy, you buy wood from forest, the larger sort of the larger trees that you can use for timber cost you about 50 euros per cubic meter. The ones that you can use for pulpwood cost you about 17, and the one that you use for energy is about 8. And of course, it also means that if you are an energy producer, you just cannot, with the current energy prices, you cannot afford buying high value wood, because you would have to pay way more than what you actually get for the end product. So the market economy also keeps checks and balances to saying that start from the forest. I mean, you have the roundwood, and then you have the barks, the tiles, for example, that you actually, my shirt could be made from wood, composites, and other structural applications. Of course, we are looking at mechanical products like timber, housing, and also to much more into more advanced products that you can actually, for example, make housing modules out of it. And then looking at the loop, where we actually take back the recycled fiber or the recycled wood, rather than burning it, we are also looking at possibilities of then giving them an extended life as chemicals, or then as energy products and basically fuels. Traditionally, the bark, the thinnings, are still used in combined heat and power plants, either in industry or in municipal power plants. But more and more we're talking about how to biorefine. So biorefining basically means that it's an analogy to oil refining, that you actually produce chemical and fuel products out of it. We're starting to see now plants coming up where they produce either energy products, typically advanced biofuels, or biochemicals. So we see this sort of a trend of actually getting from the traditional, even in the energy side, getting from the traditional CHP into more of actually fuel products, for example. And what is the reason for this? Why do we want to have fuel advanced fuels, advanced biofuels? Just because it's cool? Any ideas?
Well, that increases the energy security if it's self-sufficient, at least partial self-sufficiency.
It does. What else does it do if it's bio-based? It's for emission reduction. Basically, what we're seeing is that Finland, I don't know if you have been talking about emission trading, and non-emission trading part of the, well, basically emission trading system that's we have in Europe, right? It involves the utilities and the large industries. So basically they have to pay for their extra CO2 emissions. Then we have parts of society like housing, transportation and agriculture that are not part of that. And for example, in Finland, by 2030, in that sector, in transport, agriculture and housing, we need to reduce our CO2 emissions by 39% in 13 years. And so basically, agriculture is really difficult to reduce emissions in agriculture. Housing, to some extent. Traffic is probably the easiest. So that's why we're pushing for two things in this country, or three things basically. Electric cars, advanced biofuels, and biogas. So that's why there's a real drive now to actually start using these type of biomass into advanced biofuels. The trick is that that is, if you think about, I don't know if you have been studying or if you know how the biofuels are made, but basically there are three main routes. One of them is to use oil and fats, which is the easiest, and that's what Neste is doing. But there are just so much oil and fats in this world. The second one is to produce bioethanol from sugars, and that's what ST1 is doing. The route that takes you from bark and thinnings and let's say the heterogeneous biomass is typically via gasification. I'll come back to that a bit later. That is the most difficult. That's the most expensive route. So that's why there are not that many plants yet that are doing that, but there is a need to push into that in order to get. Actually, what the government wants is that we would have 30% of the energy that or fuels that we use in our transportation that come from renewable sources in the near future. This just to give you an idea that what are the current situation when it comes to how we use wood and how much we use it for products and how much we use it for energy. A direct use for energy is actually quite small. It's here. How we actually use wood in heat and power plants. The major part actually is the energy production in the forest industry. Any idea where that comes from? Pulp and paper. And what is actually the big mass, the big flow of? So it's actually black liquor mostly. So the black liquor on I don't know if you know how well you know the pulping processes, but black liquor is the mixture of chemicals and dissolved wood compounds that is burned in order to recover the chemicals in pulp mills, and that is actually one of the biggest sources of bioenergy in Finland. So this actually shows you two things. First of all, it shows that without having pulp and paper and mechanical wood industry, there would be very little bioenergy in Finland. So the energy production is related to production of other products, which is very important to understand because sometimes these two things are seen as contradictory, that you either use it for products or you use it for energy. You actually use it both for products and energy. And if there are no products, there is very little energy. Because what's used as energy are the residues from the production. And the second thing which is important to understand is that when we think about I would say the sustainability of biomass use, It's important to understand that about 25% of the annual growth is left in the forest. So only 75% is either used industrially, domestically, or lost otherwise. So the forest stock in Finland grows annually. And now we actually have about twice the amount of wood in the forest as what we had in the 50s. And that is important to know because that sort of gives also to some extent the justification also to use it for energy, because we're increasing the amount of carbon that we store in our forest every year.
I have a question.
Yes.
It's a fast one, so I don't think the microphone. How is that globally?
How is that globally? Globally, it looks the boreal forest, the ones in the northern hemisphere, are growing, and of course we are seeing the forest loss in the tropical forests, which is of course especially from the point of view of biodiversity, is the most critical, because that's where the biodiversity hotspots are. Here 10,000 years. There was a block of ice. There was nothing here, and everything has come actually afterwards. So there has been not enough time to have sort of these ecological niches here. But in the tropics, it's a completely different story. So basically, the big question, I don't know how much you've been following the debate now over the last year or 2 years on the use of forests to combat climate change. So there are basically two schools of thought. The first school of thought says, stop all logging. So for short-term climate benefits, we should let the forest grow as much as possible. The other school of thought says that, hold on, that's not very clever, because for longer term, in the longer term, to maximize the amount of carbon the forest can the carbon sink of the forests, you need to manage the forests. So when you manage the forest grows bigger, it can absorb more carbon, which they see is a much more sensible approach. So now what we are seeing is a public debate, which one of these should be adopted. And if we are looking at from the climate change perspective, we should of course try to maximize the amount of carbon that we lock into the products that we take from forest. So like in buildings, like in chemicals, etc., where the life of the carbon stays as long in the product as possible, thus not getting into the atmosphere. And if we are to use part of it for energy, we should be using those parts that would decay quickly in the nature. So if we leave something on the forest floor, it takes a certain amount of time for it to decompose and release the CO2. So that is now the sort of ongoing debate that I think if you haven't read it, please take a look at it. And that's also, it's not only here in Finland, it's actually European and global level. And this on the right actually shows you some of where we actually how we actually use the forest for energy at the moment. But try to maximize the carbon sink and use the ones that will decay fast. An interesting, going back to the waste hierarchy, prevent, reuse, recycle, etc. It has been proposed in Central Europe. They are wanting to apply this concept also on biomass, and it's called cascading use of wood. So you would use biomass for material, and then as material as many times as possible before it actually using it for energy. And I only took this here because what we are seeing now is a merge of sort of bioeconomy and these circular economy concepts. And this is a highly problematic concept for example, from a perspective of a country like Finland, where most of the products actually are exported outside our country. So if you have to do this on a sort of national basis. 95% of the wood that actually we make as products leave Finland and are exported to Europe, Asia, wherever they go. And again, this is something that can be seen as a limiting factor. If this is to be applied, it basically means that biomass should not be used for energy unless it has been used for material first. And again, it's a sort of a limiting factor to the, or a possible threat to the amount of biomass that we can use for energy purposes in the future. Again, an ongoing debate in Europe. Basically, what we'd like to see is that if you want to really maximize how much you actually get out of the biomass, this is again the triangle in a way. Rather than having something where you actually cascade amount of material, having a sort of a small volume material, to use it in a way that you actually use the parts that currently have no use as materials. For example, for branches, it's very difficult to make anything from branches of different trees, rather than burn it or produce chemicals out of it. You cannot really make a table or something else out of it. So really, it's about trying to use the whole tree for the purpose for its best part. So there are a certain amount of chemicals in a tree. Use those for the specialty chemicals. There are the fibers. Use them for pulp and paper. There's the bigger parts that you use for structural products, and so on, so on, so on. But this again is part of the discussion ongoing about the resource efficiency of using our natural resources. How do you make most of it? We are actually about to publish a study where we wanted to see that what would be the effect, looking at two scenarios up to 2050, and looking at our biomass resources. Do we want to use it for energy? So the climate change is the driving factor. What does it actually do for wood flows? What does it actually do for national economy? And the other one is that we'll focus on maximizing the value we get out and seeing how well that will actually also answer the questions of low carbon energy. And I think I'm sort of... and basically, so looking at that, we focus on new products. And here you can see actually how the wood is being used for different applications. I think you can see the biggest change between the CNS, which is the sort of the energy only, and the Bioeco, which is the let's focus on high value products and let's see what's left for energy products. You can see that there is a considerably more biomass ends up in energy use rather than in product use. And what does it actually mean? It means that if we focus on new products, we could, in a couple of decades, double the amount of added value that we get out from our forests. The purple line there is the existing sort of the existing portfolio of forest products, and everything above it are the new products. And of course, this is just a guess. But the point was here that if we focus on added value and resource efficiency in a way that we're still cutting down as many trees as before, we're just doubling the value out of it. We can actually gain so much more in our national economy than just focusing on pure lower value energy products. But we can also see that with both scenarios we can actually achieve considerable CO2 reductions. And here you can actually, I mean, I don't have, there's not enough time to go through all this. You can see here the timeline, the sort of three scenarios, the baseline, the 2 degree scenario with the energy only and the added value scenarios, and also where the primary energy comes from. And you can see that of course there are place for hydro, wind and solar, but biomass still even though we are focusing on higher end products, the bioenergy is the dominant energy source. Because of the production volumes, there are still the residues, the black liquors and the others left for energy products. So it's not like it's either energy or added value, it is added value and energy. You can actually achieve both worlds. This will come out in a few weeks' time, if you want to read. We also did a similar study for the food sector too. So what do we work on? On the other side of the street, we basically work on, when it comes to the residues and side streams, we work on three technologies. We work on industrial biotechnology. So basically converting lignocellulosic raw material as cellulose actually into glucose, and the glucose then through fermentation into, could be alcohol or alcohols or could be chemicals. And here the challenge really is that they're basically twofold. First of all is how do we hydrolyze the sugars? So we use enzymes. It's expensive. How do you actually make it more effective, more cost efficient? And also how do you account for all the compounds that you have in your biomass that will make life difficult for the microorganisms? So to make the microorganisms more tolerant to inhibitors. And that way you can make the economics of the biotechnology route better. So that's the two things we're focusing on. We also have two thermal processes that we work on, gasification and pyrolysis, fast pyrolysis. With gasification, basically, I don't know, I guess you have been going through gasification in some of your studies. So basically you break down the material thermally into CO, H2 and other compounds. And then you start synthesizing back again into chemicals or fuels. There the problem is the capital expense that you need. I don't know how many of you have actually been looking at there's a proposed biorefinery in Kemi, which is supposed to be based on the gasification route using Chinese technology. The production is 200,000 tons, which is not very much, but the capital expenditure is about 1 billion euros. So it is a very expensive way of producing. So you have to have a large scale in order to get the economics of scale. And what we are working on actually now are two things. First of all, trying to make it more simple. So we could actually make it more economical in the scale of around 200 million euros rather than having to build it to be 1 billion euros. And the second one is, of course, looking at alternative end products rather than just Fischer-Tropsch wax, which you make into diesel. And the third one that we're working on is fast pyrolysis. I don't know if you're familiar with pyrolysis. There the challenge really is the poor quality. The pyrolysis oil that you get has a lot of oxygen. It is a mixture of all wonderful organic compounds. And what we're actually working on, how can you upgrade that pyrolysis oil so it's actually compatible? You can actually feed it into oil refineries as a co-feed. And then you are actually opened up then you can do out of it whatever the oil refineries will do out of it. And then it can enter into fuels, into chemicals, plastics, etc. So those are the three things that we work on. And we work in lab scale and also in pilot scale. The pilot scale meaning that you need about a room this size to do the experiments. And one of the things that is sometimes also missed in the public discussion is that there's been a lot of criticism. Why do we focus on fuels? Because everybody's going to drive electric cars in the near future. Well, first of all, we need a lot of electric cars. We currently have about less than 2,000 in Finland. We need at least 250,000 in 12 years. And there's plenty of need for the fuels in aviation, in marine transportation, in lorries. And also, as you can see from this picture, you can use the same plant to start producing chemicals. It's just a different synthesis unit, and you'll start, rather than producing fuels, you can start producing chemicals. So basically, not all that investments will go in vain. But the drive for fuels gives an incentive for companies to invest. So they'll invest in the capacity, and then it can be redirected to other purposes. Another interesting thing is what we're also working on to some extent, at least on conceptual level, is how can you combine this, for example, a biomass boiler with concentrated solar power. So you kind of have a hybrid that when it's sunny and on the daytime you can actually do either, depending on what you use it for. If you use the solar for feed water preheating, it gives you a marginal power out sort of increase. But what you can also do is to have a superheating by the CSP, which means that you can then come down in your use of biomass or coal or whatever you want to do it. So try to combining because of course the issue with wind and solar is that it's dependent on the conditions. It's not sunny 24 hours a day. Not necessarily even windy 24 hours a day. So you need, for the security of supply, you might need your biomass or power plant, but this gives you at least a possibility to offset some of that fuel use with the renewables or the intermittent renewables that you have. So this is one of the things that we are working on. And there's a lot of when you look at the future of biofuels and the future of bioenergy, there are certain EU policies that are seen as dark clouds on the horizon. Sustainability criteria. What can you actually use for energy? I don't know if you're familiar with the LULUCF, land use change forests, which means about what is the climate change effect of land use change and the use of forests. So basically how carbon sinks are calculated, and then what is the baseline year. This has been a big debate over the last year, and it's still ongoing. And of course into what are the new policies regarding the renewable energy standards. And then on the Finnish side, I don't know if you know that we are going to phase out coal by 2030 in energy production. That's the plan. And of course then how to have these investments for the biofuels, etc. But really there are certain challenges or risks related to policies when it comes to bioenergy, which from a point of Finland, where about 40% of our current energy is provided by renewables, and most of that is biomass, is a big risk if we cannot use that anymore and we need to somehow replace it with something else. That was the bio part. Are you still? Yeah? Or do you need a break? No. I'm just going to briefly go through some of the waste to energy things, and I will then more concentrate on the CO2 part. But this is not something that I'm specialist in. This is actually provided by some of my colleagues. But just to sort of give you an idea that what are the wastes that are out there that could be used for energy, and also keeping in mind there are a lot of countries in the developing world where there is not necessarily a highly organized waste collection system as we have here. So there is plenty of opportunities for actually, first of all, collecting the waste and then making energy products out of it. And actually, having the energy production or the fuel production from the waste can sometimes be the best way to actually make it possible to start collecting the waste. Because there is an end product and somebody is willing to pay for that end product. And that gives you the possibility to invest in the collection of waste rather than it being dumped in random places. The traditional way to burn waste, and this has been going on for well, not for centuries, but for decades. It's a basic grate combustion. You just have a grate, and you have put there the municipal solid waste, and then you burn it using a grate boiler, and then you have a steam turbine, typically with quite low steam values because of corrosion issues, and also having a very low electric efficiency of production. And then what we are seeing more and more is that actually looking at gasification as an alternative in order to be able to produce a sort of a burning gas or fuel gas, and the fuel gas then you can use with higher efficiency. And also pyrolysis works really well on some applications like car tires, for example. You can put car tires in pyrolysis that basically you get oil back without having any of the issues of the pyrolysis all that you have with biomass. So what we're actually seeing now is sort of the trends is that first of all we're trying to improve the energy efficiency, either just the electricity, the efficiency of electricity production, trying to get into higher steam values. Obviously, that's one way of doing it. The other one is of course looking at how can we make use of the thermal energy that is available, especially in countries where you don't need it for district heating like here. But could you use it for district cooling? Could you use it for desalination, especially in places where you need to desalinate? You can use the excess heat for that. So looking at integrated concepts rather than standalone plants. The second one really is the material recovery, because basically these energy production sites could be the collection point of all waste. So you could also, rather than just putting everything into the oven, you could start sorting and trying to get the more valuable materials out from the waste stream before you actually combust the rest. And that of course improves your economics, but also improves the circulation rate of the and sort of this is the way to start implementing circular economy in certain countries. Collected, sort of a centralized collection, then starting to take out the plastics, take out the metals, etc. And of course then looking at, is there a possibility to upgrade my product rather than producing electricity and heat into making liquid fuels or chemicals out of this combustible material. And of course, if what we are working on at VTT is the gasification-based routes, and really looking at gasification of waste and looking at also the way that using the fuel gas, of course, as a fuel, but also looking at what can we get out from the ash. Because the minerals, for example, if you combust something or gasify something, you will have ash of the non-combustibles. And then how you reclaim minerals and metals out of that ash. One of the examples of what we've actually been doing, and this is based on some of the research we did years ago, is a waste-to-energy plant in Lahti. I don't know if you've actually had an excursion there. Well, if you haven't, you could. So there's a basic gasification where there's a site gasifier that produces fuel gas, and that's combusted in a boiler. And that's been working since 2012. And it's Finnish technology. Valmet is or formerly Metsä Power was the provider of the technology for this one. So what we are really seeing is that the waste to energy is really getting into as a part of waste management in general. What we are seeing is that rather than putting everything into the boiler, we're starting to sort things out. We're trying to homogenize the material that we use for fuels, and we are actually getting into what's called solid recovered fuel, which is sort of standardized fuel that you can use either in boilers, but you can also use in cement factories or anywhere where you actually have solid fuels. So this gives again a possibility to decarbonize in some countries, for example, cement production, which is one of the biggest CO2 emitters in this world. And of course, when you have more standardized fuel, you can also, you know that your specs in regard to alkali and etc. are within certain tolerances. You can then also go for higher steam values, because you don't have to worry about the corrosion anymore. You know where you stand, and then you can get into improved technologies, and you can also get a better energy efficiency out of your system. And also the SRF is really, it's a commodity in a way that you can sell it, you can buy it, because there's a standard that says what it should be. And in the longer term, what we will be seeing is that to really start producing waste into syngas and into, for example, ethanol. There's a plant in Edmonton in Alberta in Canada where they turn municipal solid waste through the gasification into ethanol. They use that as a fuel. So the technology already exists. So basically what we're seeing here in all of these topics is that we are trying to upgrade. We're trying to get to higher value products because that's where the money is. These commodity products are low value. It's not very good business unless the government for some reason supports it heavily. But if you want to make it a self-sustained business, you need to go for higher value products. And then one of the things that we're looking at is, of course, looking at how can we then use the solid residues that come out of it into recovery of the materials from there. And we have some examples, for example, from the car industry, where we're trying to looking at basically when the cars are recycled, that's a combination of metals and plastics and whatever you have in the car, and going through that with the gasification, recovering the materials from that. So basically what we are looking at is that when it comes to the waste management practices, when we move into circular economy, the material recovery will become much more important, which means that there will be less material available for fuel production, and the whole material and energy recovery has to be more efficient. And also just to say that for different waste streams, there already are industrial scale applications in the world. For the solid refuse waste, fuel, demolition wood. There's one in Finland that's been operational for almost 20 years on aluminum-containing plastic waste, for example. And what we are working on is looking at the gasification route as a way to treat these materials. And as you know, in Finland, for example, at the moment, there's basically nothing is landfilled anymore. And most of the either the material flows are either recycled or then the rest is combusted. And I don't know if you've been to the waste to energy plant in Vantaa. Yeah. Okay. You know, so there's Zen Robotics robots, sorting out the material before it goes in there. Yes. Okay, so now the last stretch, CO2. As a raw material. And how does it actually then link to the energy system change? How does it link to bioeconomy? Have you been talking about CCS, carbon capture and storage? We are talking here now about CCU, which is carbon capture and utilization. So basically, rather than capturing the CO2 and trying to store it in aquifers or in old oil wells, we're trying to use it as a raw material for different purposes: chemicals, materials, fizzy drinks, whatever it is. And one of basically there are two drivers for this. First of all, of course, is the need to remove CO2 not only from stacks, but also from the atmosphere. And the second is that there are certain concerns about the economics and also the social acceptability of CCS. For example, in Central Europe, there have been some proposals that, for example, in Germany, there would be the carbon dioxide could be stored in salt mines or sort of below certain salt layers, but the local residents are highly skeptical and they are actually against it because they don't want to sit on the top of a big CO2 bubble. So there is some public resistance to that, and of course there's also the doubts about the economics, who will actually pay for it, and how expensive actually has to the CO2 emissions be for that to become economical. We are talking then, if now we pay the emission trading system price for CO2 is something like, I don't know, 7-8 euros per CO2 ton. It would probably have to be somewhere around 100 euros per ton for CCS to become really a viable option. So alternatively, we're looking at now, are there possibilities to make products out of it, which means that the product price will be the economic justification, rather than just waiting for the policies to take place. And we can basically say that there are 4 different types of carbon capture utilization routes. What we are currently trying to do, or there have been some tests around, is that when you're using fossil energy as your source, because you need energy in order to capture the CO2 and to compress it. If you use fossil energy to capture CO2 conversion, that's what we use to test the technologies. But from the point of climate impact, it's very negligible. Because basically you are emitting CO2 from your fossil energy and you are trying to get at least part of it back. And then the more you go into actually either introducing low carbon energy and introducing atmospheric carbon, the bigger benefits you will eventually get. Until you get down to the fact where you use low carbon energy like solar or wind in order to capture atmospheric carbon into products. Then you're actually starting to see CO2 reductions in the atmospheric concentration. But each one of these topics, I mean, you still need, because this is actually the future. I mean, we'll still have a very non-low carbon energy system. So that is the long-term target. But in order to do the technology testing and everything, we might have to start with the current energy system and just capturing CO2 to prove it that it can be done. So this is basically where CO2 is used today. Urea used for fertilizers, carbonates, pigments, for example, in paper, fizzy drinks, some of it for methanol production. EOR is enhanced oil recovery. That's what they're doing in oil-rich nations. So you pump in CO2 in the oil wells in order to make the oil easier accessible. And of course, industrial gases. And what we'll be actually talking today is the novel CO2 utilization, which is very negligible these days. Any idea how large are the global CO2 emissions? How big are the Finnish CO2 emissions? Any idea? Guess? Megatons, gigatons, tera, peta, micro, nano? It's here. The global CO2 emissions are about 37 gigatons a year. The Finnish emissions are around 64 megatons. The current CO2 utilization in the world is about 3 times the amount of CO2 that we emit in Finland. And the long-term potential is 10 times that. Still, it's not enough to make the world it is again a part of the solution. And what we are actually seeing here, this is a repeating pattern. Bioenergy is part of the solution. Solar energy is part of the solution. Wind is part of the solution. CCU, CCS is part of the solution. So there is no single silver bullet. We need actually a combination of a lot of different technologies, and we also probably need a change in our behavior, which is probably the hardest part.
And all of that is happening too slow.
And all of that is happening too slow. So I guess, I don't know if you read the news, was this week or last week, where they said actually now the rate of increase of CO2 concentration in atmosphere is faster than ever. So we're getting into, there should be a certain sense of urgency here. But these things take a long time. I mean, if you start developing technology, it can easily take 10 years, 15 years from your idea into industrial production. So if we came up with the revolutionizing technology, to have it ready, commercially implemented, scaled, it'll take decades. So I hope I didn't spoil your day, but and here are actually some of the things that are happening now in the world when it comes to using CO2. One of the concepts that has been tried, especially in Germany, and also we are also doing it here in Finland, is called power to gas. Why do we want to use power to gas? I mean, why do we want to use electricity as a source of energy or store electricity as a fuel or gas?
Because it's easier to store.
It is easier to store, and it comes down to the fact that what's happening in Germany?
Negative electricity price.
Yes. So basically, there's the Energiewende taking place in Germany, where they're heavily investing into solar and wind, which means, and they actually have the goal of basically being fully dependent on, or sort of that the renewables at some point will provide all the energy, and because that it's intermittent, the sun doesn't shine during the night. The wind doesn't blow on calm days. You need to have an excess capacity in order to also satisfy the need on the days where it's not very sunny and not very windy. But when it's sunny and windy at the same time, you have a huge excess of electricity in the market or in the grid. And then you need to store it somehow. And one of the ways to do it is to store it in chemicals. And rather than store it in the batteries or some other means, this gives you the possibility for long-term storage. If as a fuel, you can, for example, in Finland, in the summer, you could be producing fuels that you use in the winter. That way, storing the electricity from sun into a product. And this is especially interesting in Germany because they have an extensive natural gas network. So you can feed it into natural gas network and use it in the chemical industries, in the power industries, etc., and providing a green product for them. So Audi has been one of the first ones to try this on a demonstration scale, and they are looking at this as a potential, again in Germany, as an alternative to biofuels, are these so-called electric fuels. Other alternative is to use CO2. Some of the microorganisms love CO2. They use it as an energy source. Rather than using sugar, they use CO2. And there's this actually a New Zealand company called Lanzatech, which produces then chemicals by actually through what's called gas fermentation. They sort of ferment CO2 fermentation. And I think they have a plant right next to a steel mill. So taking the CO2 from the steel mill and then using that to produce chemicals. And what we're seeing actually that one of the topics that are in touch here are, of course, using carbonization to produce materials. That's also one of the routes that has been studied in Finland as a potential CCS concept, to tie the carbon dioxide into minerals. And here you can see the darker the green, the higher the maturity level and the market. The TRL, I don't know if you're familiar with the TRL. What it means, it's a technology readiness level. Again, another piece of jargon that you'll probably get familiar with in later stages of your career, if you get into research and development. 0 means that I just have an idea. 6 means that I've tried it in a scale like this. 9 means that I already have a plant, industrial production plant. So there are routes that are promising. The real question is that, again, where are the economics? Where are the economics in this? And actually then, in the case where you used electricity as a sort of the main source of energy, how ecologically and environmentally friendly is that? So you can see what is actually the real CO2 reduction potential in it. One of the concepts that we've been working on together with Lappeenranta University of Technology is called Solitaire, where we have a container. The MOBSU is a mobile synthesis unit, produces Fischer-Tropsch wax from CO2 and hydrogen. There's the electrolysis unit that produces hydrogen. The DAC is a unit that captures CO2 from the atmosphere. And then we take the electricity from renewables, thus producing fuels from air, as seen here. And again, seen as an alternative to an alternative way of actually storing electricity. Not very cheap. That the production economics on these now heavily depend on the price of electricity. And of course, if you had the negative electricity prices said this is very profitable business, but unfortunately, the price of electricity over the year is not all the time negative. Another thing what to look at also is that how environmentally friendly is it? And that depends on your electricity system. So what are the grid emissions? So what is the average emission of CO2 from your grid? And here you can see some of the countries. Germany, despite of all their Energiewende, they are still quite dependent on coal and natural gas, has actually quite high grid emission level. Whereas Sweden, having basically hydro and nuclear and bio, is very low, has a very low grid emission. And of course, the lower your grid emission, the lower you can actually see that what sort of grid emission you need to have in order to sort of satisfy certain standards. The fossil fuel comparator is the black line, so you have to be below that to have smaller CO2 emissions than the fossil fuels. And if you are then below the red 2 line is the 70% CO2 reduction as compared to fossil fuels. So if you want to truly be an advanced environmentally fuel, you have to be below the red line. And these are just different types of products that you can make out of it. But more or less it says that in Sweden things are fine because of the very low grid emissions. But already in France you would have to come down in the grid emissions in order to make this truly environmentally friendly. So you need to rely, if you want to make environmental products out of CO2 and electricity, you need to have a very low CO2 emissions from your electricity system. That's the point. Another alternative route is then the biological route, that you actually have the bioorganisms producing you these. Rather than doing the chemical route, there's also the biotechnical route. And this is I mean, I got actually the same education background as you guys. So I studied energy engineering here. Did one course in chemistry, inorganic chemistry. And now I'm actually in charge of people who work a lot on organic chemistry, on biochemistry and everything else. So I'm trying to sort of get the grips of this. So just my advice to you, study chemistry. It pays off. But so basically some of the routes that you can take through sunlight basically into products, either via plants. So you have so you're doing the photosynthesis, or alternative routes. And this is just to show you some of the routes that we are currently studying. And you can see that there are quite big differences in the energy efficiency from sunlight to raw material depending on how you do it. If you do it by algae, you get about 5% because algae grow fast. 5% of the energy you can get back in the products. If you go through plant biomass via photosynthesis, it's typically less than 1%. Because photosynthesis has an efficiency about 2-3% max. But if you go through solar power, which has an efficiency of 30% roughly, then you can actually get into efficiencies around 10% into products. Which means that you are much more efficient in transferring the energy. And obviously, those are the more interesting routes that we are looking at. And here are just some of the products that you can make out of it, either energy products or then sort of more advanced chemical products. And also see some of the amounts that are produced. But just to give you an idea of the routes and their efficiencies, and where actually what are being studied at the moment. And this is actually a very interesting field at the moment, because not only we are using this as a production mechanism, we also learned through engineering to tweak the DNA of these production organisms to produce whatever we want them to produce from whatever we want them to produce. And it's called synthetic biology. And actually one of the most exciting things that are happening when it comes to production process development. We are also using this route to produce food. Bit of nitrogen, bit of CO2, bit of electricity. You get protein. And this is something that was, these are actually from last summer when we came up with the concept. And we were now producing something like this much. We're hoping to produce in near future maybe kilos. But then again, this gives the possibility, if you have unlimited solar resources and a bit of nitrogen, you could start feeding the world without actually having to grow food on fields. So it's actually, and another exciting, which is a bit off topic, but relates to this, is there's a lot of exciting development going on how to produce proteins in reactors. Like milk without cows, eggs without chicken, etc. Just through fermentation. And here's the concept. So basically this was, I mean, a sort of assorted collection of bioenergy, thoughts about bioenergy, thoughts about resource efficiency in bioenergy, thoughts about waste to energy, how to use CO2, where the world is going in that field. And these are just, I mean, it wasn't me who's done all the work. These are my colleagues who've actually done the hard work. I'm here just the talking head who's presenting their results. But thank you for staying awake. Thank you for posing a couple of questions. And I guess we have plenty of time now for Q&A. It could be from this field or from any other field where I could be of help.
Okay, but let's thank our speaker.
There's a lot of stuff.
So
yeah, it's fine. It's actually for the
So in this Saltair project, it's been discussed a bit, like some of the outcome of that, and especially what Lappeenranta, some of the projections, like about the capability of this. Like for example, for each power to gas plant you put up, the more challenging the economics become. Do you kind of agree with the results they suggested regarding the potential of this technology?
To be honest, I haven't been really studying the results that you are referring to. It's very difficult for me to comment on that. But basically, a couple of things that I want to point out. First of all, I think there are several challenges. One of the challenges that I see when it comes actually to the fact that we will have a world where we have a lot of excess capacity and a very low price of electricity is that who would invest in a world like that if you don't get proper return on your investment? I think that's one of the topics to be discussed. The second is that actually I see the biggest benefit from the solitaire type of approach in connection with another biofuel production plant. So, for example, if you have a bioethanol plant, the one of the byproducts is CO2. So, with that CO2 and with the electricity, you could boost the production of the existing plant, rather than having these sort of standalone plants. Was there anything new in this? Or was it the same that you already heard in your lectures?
So about the pyrolysis oil, you said that there's been some challenges with the quality.
Yes.
But like, is it even close, or is it maybe able to make it like to comparable with the raw oil, so that you can really make all the products that they make from the
there are two options. Basically now what the issue is that if you make it from biomass has a lot of oxygen, and the oxygen will be present in the bio oil. Of course, if you make the pyrolysis oil from car tires, it is like mineral oil. But if we talk about the biomass part, right? So now we have an oil that has a lot of oxygen. So basically, there are two options. Either you put in a lot of hydrogen to get rid of the oxygen, and then the quality improves, but it's expensive. Or you try to find an alternative like catalytic pyrolysis to improve the quality of the oil, and then get it at least close enough to mineral. I don't think we'll get exactly as mineral oil, but close enough to mineral oil so you can blend, 5%, 10% into the oil refinery, and it'll still work fine in the crackers and the other unit operations.
So the fast pyrolysis is different than doing the gasification and then
So fast pyrolysis is basically what you have is you take a small particle into around 500 degrees and it reacts in a second or 2 seconds. And basically what happens is you have the volatile compounds. So you have the pyrolysis, which is the volatile compounds get out, and then you condense them later. And the char is left, and the char you actually you burn. So that's what happens in pyrolysis. In gasification, more you convert all your biomass with a higher temperature, with a bit of oxygen, but not much, into CO, H2, CH4, etc. So it's a different thermal process. Pyrolysis is inert.
Yeah, I thought that the pyrolysis was like the next step from gasification.
No. Actually, it's sort of if you have drying, which is if you have low, you basically get out of water. Then you have torrefaction. Then you have slow pyrolysis, fast pyrolysis, and then you have gasification. Just how much you actually get the volatiles out, and do you convert the char into something or not? So there's sort of, and in a way, pyrolysis is a lower level, but it's also a much cheaper technology than gasification.
You mentioned this integrated concepts, so how to get these technologies to synergistically work together, and I guess there are many steps in the path of implementing something like this. Are there some methods or some good literature you could recommend or something?
I think if you look at the, I guess you were referring to the CSP hybrids.
In general, finding the synergies between these different methods. Is there some like developed method to evaluate what could work together the best way?
Basically, I don't know how. Basically, I think what we, for example, have been doing is just using modeling to dynamic modeling to see that in a given day how much actually you can. Does actually the process work? Given the amount of sunlight, for example, you can actually design it in a way that you can superheat it, and then you can simulate a day to see how much you can actually produce with the solar, how much you need biomass. You can also look at that how flexible is your boiler to cover sort of part loads. So I would use. I mean, of course, you could use some sort of analysis to see that how much on the average day you get sunlight and how much you can sort of absorb it. But I would sort of start quite soon building a model and testing that out to see where are the limits. Because there are also limits. On the first one, actually, basically what you're doing is you're just running your boiler at full load, which is easy. But with this, you're actually running it at part load. And how well can you actually run it at part load is a question. But that is also something which is happening to conventional power plants now when we are getting more and more intermittent renewables in the system. The power plants that used to run the base load are now being relegated to balance the load, which means that they are ramping up and down, which is not something that they were designed to do.
Yeah, just a comment. One good source is to go to a master thesis from Suojanen, done with VTT actually, okay. And Tampere University of Technology.
Good, thanks. Awfully quiet. Is there coffee available? No? There were some coffee cups outside the... Yeah, please.
Well, since having this amazing opportunity, then why not to use it? About these electric fuels,
yes.
Do you see it as a realistic future scenario? Because some of the future researchers have suggested that because of the solar cell technology getting so much cheaper all the time, that it wouldn't take maybe so long to have a lot of excess electricity available in case we can store it. So in that sense, the conversion process efficiency wouldn't maybe anymore count so much. But is there a lot of opportunities to reduce the investment costs in these synthesizing plants, for example? Is it such early stage now?
Well, basically, if you look at this solitaire concept, it's actually made from commercially available components. The synthesis unit is of German design, but there's a company that makes this, and I'm sure it can be upscaled from this. Electrolyzers you can get, I mean, that's proven technology. The only thing is that you don't get very large electrolyzers, but you can put them in series. And the DAC, which is the direct air capture, is not something that you probably do. You would probably get CO2 from a CO2 source rather than trying to get it from the atmosphere. And of course, you can get then the electricity from the grid. So in that sense, the technology is you know, it's already, at least to some extent, commercially available technology, just combined in a novel way. Whether it will ever make a difference, it depends really on I think this is sort of if I remember right, you know the biodiesel plant in Lappeenranta by UPM produces diesel from tall oil. Well, produces about 100,000 tons of fuels, which is something like a few percent of Finland's fuel use. If you were to do that production using this concept, the average power demand would be something like 300 megawatts of electricity. So you need a lot of juice to do this in large quantities. So then again, the idea of actually having this in connection to an existing plant where you could sort of turn this on and off, depending on the electricity price, probably makes the most sense. And these are concepts. We'll see on how well these will fly. And of course, there are a lot of things that affect. Of course, the price of electricity in this is the crucial key to the economics. And of course, the other one is what is going to be the price of oil. Now, because price of oil is what, $40 a barrel, something like that. None of these are very economical compared to fossil oil. Most of these actually have somewhere, the break-even point is around 100. If the barrel of oil costs about $100, then these start to be economical. I mean, roughly. I mean, there are certain technologies that are cheaper, certain technologies that are more expensive. But it's very difficult to compete in these conditions against fossil oil. And that's why, for example, in Finland, we have a mandate. There's a blending mandate that you need to have a certain amount of renewable fuels, which means actually that within that blending mandate, you don't need to compete against fossil oil, because that part of the market is only for you. What you need to do is to make sure that you are the cheapest option of the other options. That way you can sort of provide the incentives to invest in something like this or the biodiesel plants.
Okay, thank you very much.
All right, thank you.